Hello, chemistry students. Last week, you became experts at electron configurations, but I just can't have you going forward in your chemistry careers thinking that electrons fill these perfect boxes and there's never any deviation from those electron configuration rules. Of course there are, and we're going to talk about some of the ways that electrons play games to become more stable than the original electron configuration that you would predict. Some examples of metals that do this very commonly, they can become more stable without gaining or losing electrons. Those are copper, gold, and silver. So what can you tell me about copper, gold, and silver? Please describe some common uses of these metals. Alrighty, let's look into their electron configurations. I have written them out right here. What do you notice about copper, silver, and gold? What you should pick up on is that right here at the end, the 4s is not full, but the 3d is. That's copper. For silver, the 5s is not full, and the 4d is. And then finally, gold plays the same trick. The 6s is not full, but the 5d sublevel is. If you were writing out these electron configurations just giving the chart that I gave you last week, you would not have written 4s1 3d10, you would have written 4s2 3d9. So today we're going to talk about why a half full S sublevel and a full D sublevel is more stable than this. Okay, so the most stable that an electron configuration can be is if there is a full octet. Next, if there is a full sublevel, that is a stable electron configuration, and the electrons probably aren't going to move around. Probably. Depends on the sublevel. And the next most stable is the half-filled sublevel. And finally, the least stable electron configuration involves an unbalanced sublevel. So if we were just looking at the p sublevel, well, obviously you guys know what an octet is, so I'm going to skip that one, but a full p sublevel looks like this. A half-filled p sublevel. You see how that's nice and stable and all of the electrons are spaced out evenly. Now the least stable that a sublevel can be is if it is unbalanced. I'm going to give you two examples of unbalanced sublevels. Both of these are p sublevels. This one is unbalanced. And this one is also unbalanced. So let's use this information to describe why those metals are more stable with the altered or unique electron configuration. Just give me a second to fill in all 79 of gold's electrons. Okay, so our predicted configuration ends in, we'll call it 6s2 5d9. So here's what we have predicted. So the 6s is full and the 5d is unbalanced. Okay, so now let's play the game where this electron pops over and fills up our 5d. Now we have our unique configuration. We'll call this one 6s1 5d10. So in this situation on the table, our 6s1 moves up to half filled. It was full, now it's half filled. But the unbalanced configuration moves all the way down to full. So overall, the entire electron configuration is more stable because you're getting rid of that unbalanced sublevel. Okay, let's do one more example with ruthenium. Ruthenium has 44 electrons. Okay, so we are paying attention to the 5s and 4d sublevels. In our predicted configuration, we have a 5s2 4d6. Okay, so the 5s2 is full, but the 4d6 is unbalanced. So that's where we're starting our configuration off at. Now, what do you think is going to happen here? Ruthenium does actually lose an electron, and its oxidation number is ruthenium plus. So this element has 2 valence electrons, but its oxidation number only has 1. This is because it is more stable when the electron in the 4d orbital, let's erase it all together, disappears. You see that? So with that electron configuration, now here's our oxidation number. Or oxidation configuration, we'll call it. It still has 5s2, but it has 4d5. And that is because it is more stable to lose that electron and go down to a full sublevel and a half full sublevel, because the 4d is exactly half full now, than it would be if you got rid of those 2 electrons in the s orbital. Then you would have an empty sublevel and an unbalanced sublevel. And so this is just the preferred oxidation state for ruthenium. I wanted to show you this just so you were aware that things do deviate from these perfect little rules I gave you, but I don't want you to stress out because most of these deviations happen when the d orbitals get involved with the electron configurations. So all of the electrons, or all of the elements that use the d orbitals are right here on the periodic table. You'll talk about them in more depth in the next chapter, but all you have to know for now is these are called the transition metals. And they are very unique in their electron configurations. I also wanted to point out that most periodic tables will give you common oxidation states for transition metals. So look at iron, the example they gave you, it has 2 common oxidation states. So there are 2 ways that the electrons shift around in order to become stable. I will definitely give you plenty of warning if there is a strange electron configuration in the mix, but for the most part, just follow those rules that I gave you last week and be aware that sometimes these guys in the middle, they can play tricks.